So let's welcome our first speaker, this afternoon, Ben. He will talk about the FRB, progenitor models, and so on.
Wow, okay, I'm completely outstaged. I just feel like using this whole hour just asking you guys more questions. Well, okay, I'll continue calling the repeater as well. So I guess have to find some other naming conventions. So thanks for inviting me here and having me here. As my title says, I'll talk a bit about the progenitor side. From the observations of the theory. I'll try to give a current sort of state of what we think the progenitors might be, and I'll try to convince you that things have changed dramatically in the past couple of years just because of the repeater. And so it's not really an anything goes thing anymore. So I'll focus a lot specifically on the magnetar model, or what I call the concordance magnetar model, because I'm biased to that type of model, but I'll mention some other models as well. So just a brief outline, I'll start with basically confronting theories of observations. I'm trying to show that, out of the building theories proposed so far, actually most of them do not hold water if you want to explain the repeater. I'll give some comparison to the GRP field, basically loosely based on trees very nice vertical recently. I'll then go to some of the details about where the clues point, try to convince that magnetars are appealing models, and then describe a specific magnetar model and how I envision how things might go. And then I'll conclude with basically the current state of affairs and move forward. Okay, so if you want to have an FRB theory, an FRB progenitor theory, and it wants to be successful, you obviously have to explain the observations. So what must any FRB theory explain? Obviously the time scale, milliseconds, frequency, gigahertz, the energetics, if they're extragalactic, range of 1038 to 40 hertz or so. There's also the dispersion measure, which is of course what indicates that these might have been extragalactic before the first localized FRB. And so these were sort of, the old game. These were the first observations at the time when we had, the first burst, the Lorimer burst, and the Thornton sample, and all of those early samples. And in that time, theorists really went wild. Because there's really not many observations. So basically, lack of constraints allowed us to pretty much get away with anything. And so here's sort of a brief rundown of various different models that have been proposed. This is not exhaustive. There are many more that I even did not include here. But I've sort of categorized them into terrestrial phenomena, galactic, cosmological, and nearby for galactic and cosmological, so it's sort of a distance scale. And at first there was discussed whether or not these are actually real phenomena or sort of just RFI, terrestrial things, microwave things, which we love now. Of course, there were galactic. There's a big debate whether they're galactic or extragalactic. So there are various models of these are just flaring stars, up to different cosmological models, cataclysmic events like binary star mergers or mergers of anything you can imagine. Why not? We love mergers now that we have LIGO. Black hole collapse of blitzers, and various other phenomena. So, we have this whole barrage of theories, and people like to say these types of things. We have more theories than bursts, or I'd even go one step further, thanks to a few prolific theorists. I think we even had more theories than theorists working on FRB, which was true at some point. And other statements like it could be anything, or maybe even worse, it could be everything. Right? And so this is sort of a pessimistic kind of outlook on the theory side of things. What is it even worth if we're just throwing out these ideas and none of them are actually constrained? And so what I'd like to try to convince you is that none of this is true anymore, given the past couple of years' observations and given what we know about their behavior. And so I think you should throw these notions away and really focus on what the current observations tell us. So if I go back to this list and continue, well, we now know have some idea of the rate. There are some big error bars here, but order of magnitude. And more interestingly, we know much more from the repeater. So FRB 12.2. So we know that it repeats, of course. That's an important thing. It tells us that these are probably not cataclysmic events, at least not the ones that form the repeater. We also know that the repetition is non-Poissonian. There's a rapid recurrence time between successive bursts on some occasions. We have amazing polarization information now. So we know that this first has a huge rotation measure. The rotation measure evolves in time quite rapidly. Their bursts are linearly polarized. There's a constant polarization angle. So it's a wealth of information about constant polarization. Also, given the fantastic, work localizing the repeater, we know that there's a persistent radial counterpart. So this source that Sarah was mentioning earlier, it has, this quite large luminosity, actually, not something that I think anyone would have expected to see. And you have to explain the luminosity and spectrum, emission size, so there's some constraints on the emitting region that produces this radial counterpart. All of this has to be explained by any successful FRB theory that wants to produce a repeater. In addition to the host galaxy environment, which is again something that I mentioned, we know that the repeater is in this rare metal core star-forming dwarf galaxy. And I'll go into that in a second. And the last piece of information is, maybe there should be a question mark there, but the DM doesn't seem to evolve, at least not significantly over the observational baseline that we've been observing the repeater. And so really there's a ton of observational constraints. And if you go back to the list of theories that I put up earlier, most of them just don't work. Should also, put this statement down here. I would say that any successful, or worthwhile FRB theory should not only explain all of these phenomena that have been observed, but should also, provide some predictive power to make it falsifiable and, to see how it fits with future observations. And so this is what I just said. Most theories are really ruled out by the repeater. So, how is the field of FRBs advancing in comparison to GRB? So this is a nice plot from Shree's review article in Nature just recently. And what you see here is the number of publications in dashed and citations divided by 10. That's the solid. And this is for FRBs. This is a function of here, the number of citations in publications. And this is for GRBs. And here the timescales are from 1975 to 1995. So basically, GRBs went through a very long period where things just sort of were on slow burner. There weren't many publications coming out, not many citations, and that just had to do with the fact that there weren't many new observations coming in. You had to wait for, well, not me, but whoever was working on these at the time had to wait for observation facilities to come along. And on the other hand, for FRBs, we have this dramatic increase in the number of papers and citations just in the past couple of years, and this is mostly again due to the discovery of the repeater, its localization, discovery of its rotation measure, and persistent radio counterpart, and things like that. So there's a much faster evolution of the field, and some lessons that we should take from the GRB field is, besides that we're lucky we have a much faster evolution of the field. We also had, the settle of cosmological versus local. So that was sort of settled quite early on, just took decades in the GRBs. Some other lessons. It could be that the emission mechanism of FRBs may be, debated for a long time, even long after we understand or think we understand their progenitors. That's true of pulsars, of GRBs. There's still lengthy debates on those processes, whereas we think we understand much else about those. And then the last thing, which is multiple populations, which is something everyone likes to focus on nowadays. So I'll give you my 2 cents on multiple populations and what I think. So my current view is, are there multiple populations? Maybe. I would be highly unsurprised if there were, given what we know about GRBs and given the fact that basically we have new observational capabilities, so quite reasonable that we'll discover more than one phenomena with these similar observational characteristics. But on the other hand, I don't think there's any evidence at the moment that necessitates multiple populations. And so just by that alone, I would say that by Occam's razor, there's no reason to assume at this point multiple populations. So in other words, I would say that the repeater FRB 121102 is perfectly consistent with the fact that all FRBs are pretty much produced by more or less the repeater or some version of it at the moment. And so even though again, GRB history suggests that there may be multiple populations, I think this should never be used as an excuse for poor theory. And in other words, here's to try to explain what is observed. And so most of what is observed and most of the information constraints that we have are from the repeater, rather than try to hide behind what isn't and explain, okay, we know nothing about the other verse, so maybe there's something. Sure, but that's sort of just, kind of shined away from the observations. And then I have this nice quote from Drew's paper. I'll just read it through because it's a really cute joke. So in preparing this comment, this is for 3, I experienced deja vu. The modus operandi was astonishingly familiar, suggests all possible collisions between comets, asteroids, count wars, white dwarfs, neutron stars, and black holes, invoke improbable scenarios, and failing all of these possibilities and roads to the theory. The expected diversity of FRB classes should not be used as license to speculate presence. A worthwhile model does not violate. You get the point. So again, my take, again, this is my 2 cents, I would say that it's very likely that there are multiple populations, but I would say that we should try to explain what we know and not what we don't, which is the repeater. Okay, so where do the clues point us given these observations? We'll start with the host galaxy, which is something that Sarah mentioned earlier. So the host galaxy, which is this low metallicity dwarf star-forming galaxy, is highly suggestive that maybe these events are somehow related to superluminous supernova and/or long GRBs. And that's interesting because both of these phenomena have also, on theoretical grounds, been invoked to be powered by magnetars. And so, why is that? So, first I'll show you some observational plots. So here are plots from a paper by Milan, 2014. Basically, this shows that long GRB hosts and superluminous supernova hosts track one another and are markedly different than core collapse supernovas. So in other words, superluminous supernova and long GRBs occur in these rare, quite peculiar environments, not where most of the star formation in the universe is, not where most of the core collapse is, not where most of the stellar mass in the universe is. We just pick our star by random, the universe will never fall in one of these galaxies. It's quite a peculiar environment, so it's not just a chance, it doesn't seem like it's a chance to live. Again, we have an n=1 sample size, so anything can be chance, but it's highly suggestive. Where does the repeater host galaxy fall in all of this? So you probably can't see the labels, but these are just plots of the absolute magnitude of the host galaxy, stellar mass, star formation rate, and metallicity. And the takeaway is just that the repeater, which is this star, sits smack in the middle of the population of the red and blue dots, which are supernova and long GRB hosts. And if there was to plot core collapse supernova hosts, they fall in a very different region of the planet.
Metallicity, which way does it go up? High is low, low is high?
Metallicity here.
Unit on that? Yeah, what does 8 mean?
Oh, so 8 is a higher, so this is low.
And solar would be what?
I forget. Solar is someone in the crowd must know this. Low? Solar metallicity? Low? Yes, I think they're under that, but low. Grateful to Great. Okay. So these are the host galaxies. Just a brief aside on superluminous supernova and long GRBs. Give a whole separate talk about that. But again, just to convince you that these events do need some energy source. So these are transient events. Superluminous supernova are just very bright supernovae. And the point about them, the main takeaway about superluminous supernova is that they are so luminous that they cannot possibly be powered by radioactive decay of steam. And so you need some additional energy source to power the light curve and millisecond magnetar, so basically a neutron star that has high dipole magnetic field that's rotating sort of at millisecond periods has been invoked as such. And here you see one example of supernova that's 2015 yen with fits to the broadband data, and these are fits with some magnetar properties and seems to work pretty well. And similar things have been done for GRB as well. And so already this first piece of information is suggestive. Okay, maybe magnetars have something to do with all of this. What else? So repetition. I mean, obviously repetition tells us that this can't be a cataclysmic event, at least not for the repeater. Unless you can explain, multiple cataclysmic events preferentially happening in some environment, which may be some levels. Also, the rate of the FRBs can be made consistent with the birth rate of magnetars that form supernovae or long GRBs. So these two events have sort of comparable rates, more or less. And the FRB rate can be made consistent with the rates of these two transients, using a lifetime of 100 years or so with our activity. By the way, another interesting point about repetition is just the first fluence distribution. If you look at the distribution of fluence of just the repeater, it sort of goes as DRD is like e to the minus 1.7-ish, which happens to be sort of the power law that first of SGRs or anomalous X-ray pulsars follow. So this could be a complete coincidence. I've heard people mention that this is also a power law for the energy or something, or the some measure of earthquake activity. So it could be completely coincidental, but that's something to keep in mind. What else do we know? So rotation measure. Rotation measure obviously tells us that this is a highly magnetized environment, but not only so, that it's a highly magnetized electron ion environment. Just had an electron positive environment, rotation measure would cancel out. So that's an interesting piece of information in your screen. Of course, most of the time scales, you can say, okay, the time scales neutron stars are order milliseconds, so sort of makes sense then go neutron stars and based on that. And then the last point is that the persistent source luminosity is extremely powerful, and if you just wanted a neutron star to power this luminosity by spin down, and you want this to be, they're here to be whatever, 30 years old or 100 years old or something, you just don't have enough spin down power. So this is probably not rotation powered, which maybe differentiates it from normal pulsars and makes it more of a magnetar. The reason magnetars are called magnetars is because they have these extreme magnetic fields, and a lot of their energy can be basically stored in the interior magnetic field, which is then dissipated. So all of this, at least to me, sort of is suggestive that there's something here that smells like possibly a magnetar. And that's the model we'll focus on. So here are the schematics of how to create a magnetar model. So there have been many sort of those ideas, and this is all based on the work by Barsky and Dov, and others, which I haven't listed. But it is the following. We have this magnetar. It's young, presumably, very active, so it was recently born. How young? Unclear, although that assumed, but maybe 10 years old, maybe 100 years old. This magnetar inflates some nebula around it, which I'll explain in a minute. But all of this sits inside the supernova ejecta, again, because this magnetar is young, 10 years ago or whatever, the supernova that formed the neutron star happened, and so still this magnetar sits inside the ejecta. And so the idea is basically the following. You have some flare triggered by the magnetic activity inside the neutron star core, and somehow this flare manages to activate matter from the neutron star surface. So you have some outflow that is very unloaded and magnetized, which is ejected from the neutron star surface, and this outflow is basically expelled and shocks with previously ejected flares. And the idea is that, one idea is that the FRB itself produced the synchrotron laser emission within these shocks. So this is the idea that was first proposed by Barsky and by and although there are various issues with whether or not that can actually happen, this is one idea floating around. I will not focus so much on the emission mechanism itself, because my personal take is that I know that the semantic whether or not will resolve this anytime in the near future, but also because I personally have not worked on that directly. But what happens after you shock the material and presumably get this FRB? Well, basically, you inflate this nebula with magnetized, with magnetic field and electrons ions that you ejected and expelled from the neutron surface. So you have strong magnetic fields in this nebula and electrons that are very energetic, basically bouncing around. What do these electrons do? Well, of course, with the electrons in the magnetic field, they emit synchrotron radiation. And the idea will be to try to reproduce the persistent source through these electrons. What else could these electrons do? Well, as these electrons cool and their Lorentz factor is reduced to order unity or so, they can contribute significantly to the rotation method. Again, you have a high magnetic field, you have a huge amount of electrons, And the only trick is that you need them to be sort of non-relativistic, because rotation measure is inhibited by 1 over gang squared at high line spec. But the idea is that the same population sort of naturally, or presumably the attempt is that they will naturally produce both the rotation measure and the persistence source.
So what's the constant optical depth of this nebula?
The constant optical depth. So at early times it's thick, but at later times it tends to interest itself.
So that's in unity.
Yes.
And the whole thing is expanding at speed of light.
Right. So the whole thing is expanding. So this supernova ejecta is expanding at whatever the progenitor of the supernova was. If it's supernova, then presumably 10,000 kilometers per second or so. And the nebula itself is expanding just based on the energy that is inflated inside of it. In our actual modeling, we use sort of simplification that is just expanding at constant velocity, but you can do the full calculation where it expands based on the energy. So this is not at the speed of light. This expands. Basically, you just solve for sort of kind of energy organisms for an extension, sort of a set of type calculation, and you see the expansion. I'll show constraints in the extensions.
And just to see if you compare this with a crab, which is a similar setup. So there is usually the structure people say is there's a reverse to have a contact. Which of these snap to which?
Yeah. So this is the termination shock. This is the forward shock between the nebula and the supernova ejecta. And there is also contact discontinuity here, and there's reverse shock.
And all your B field is on the inside of the contact.
Yes, the B field is entirely inside this nebula.
But inside the contact even. So that there are two regions in there.
Well, you don't actually care about the surface of the shock because we don't need the electrons. So the usual picture with synchrotron radiation is sometimes that you have matter throwing into some ISM or something, and then you accelerate electrons at the shock front and produce synchrotron radiation there. This is actually a different picture. We don't care about the shock front itself. These electrons are being injected by the source. And so these electrons are not, being constantly accelerated, they're just being dumped in by the source.
But you are saying that there are two regions in this of the yellow.
Yes, there's a contact discontinuity and reverse shock on the other side.
That's right. And the B is all on one side of it. Like there's a boundary for the B field.
Yes, there is a boundary. Okay, this is the nebula part. And again, the idea is that you accumulate the rotation measure within the nebula. A second part of the picture is what happens as the FRB propagates to the supernova ejecta. So in principle, the supernova ejecta can basically either completely absorb the FRB through free absorption, but it can also add to the dispersion measure of FRB. And as I'll show, we actually want that to not happen in order to see the FRB and obey the constraints on the repeater. So that actually imposes some constraints on the model. And then in this picture, the first and system first propagate outside the supernova ejecta, and most of the dispersion measures accumulated in the host galaxy of the source and in the IGN. That's sort of the picture in mind. So this is again just sort of a summary of everything. Again, Magnetart flare ejects some matter, matter shocks, inflates some nebula at the shock front, you produce the FRB by some maser. And then within this nebula, you have a population of relativistic electrons hiding in the field, which is synchrotron radiation, which is the persistent source, and also you accumulate this rotation. And so this is why we call this sort of a concordance magnetron model, just the idea that try to explain everything with one source, and not invoke some other external population that creates the persistent source or the rotation measures coming from some other medium that is unrelated to the first of all.
And where does the millisecond time scale come from?
Sorry, where's the millisecond?
Yeah, the last bullet somehow you need the millisecond.
Yeah, so that has to do with detail of the maser emission. So yeah, I won't go into that, but I mean, if you follow the Barsky and Goldberg, you see that there is a parameter region where it works. So you need a certain Lorentz factor for this matter, and you need a certain radius of the shock at which the shocks occur, and you get the right frequency. But I agree that it's not completely true.
It's just the radius divided by the Lorentz factor square?
More or less.
Okay.
Okay, so I'll spend a couple slides just talking about what happens as the FRB propagates to the supernova ejecta, and basically what happens in this region and what constraints we can from that. So as the FRB propagates to the supernova ejecta, you have some ionized component of the ejecta, which presumably will always have some ionized component. The question is how much. Then that ionized component can lead to free absorption, and to local dispersion measure. And it turns out that you can use the lack of an observed change in the dispersion measure and the lack of observed free-field absorption to constrain the repeater's age. So just an aside to talk about the sources that can ionize the supernova ejecta, there are basically things you can think about. One is just the interaction of the supernova ejecta with the external medium. This is basically as the supernova ejecta, or the supernova around it, it shocks the ISM around it, and you have a reverse shock traveling into the ejecta. That reverse shock heats the matter and ionizes it. And if you just plot the dispersion measure, which is some measure of the density, but also of the ionization fraction that you get within the supernova ejecta as a function of time, then you get something like this black curve. So early times, on timescales of 10 years or so, you get very low dispersion measure, presumably just by this interaction with the ISM. But on much longer timescales of hundreds to thousands of years, which is basically the set of Taylor timescale of the ejecta, then the reverse shock sort of propagates through most of the ejecta, you ionize a significant fraction of it, and then that can contribute more significantly. Of course, the trick is that even though you ionize a lot of matter at 1,000 years, the density is very low at 1,000 years because supernovas expand. So you still don't get too much dispersion measure of free-field absorption. So this is order unity. This is 10, 100. On the other hand, another source, possible source of ionization is photoionization by the central engine itself. So if you think of this energetic magnetar sitting in the middle, it's very emitting a lot of radiation and basically sort of Berkeley, emitting huge amounts of energy. You can think that some of that energy would go into photoionizing the ejecta itself. And for certain parameters, that actually can be dominant over the shock heating, at least on early timescales of up to 100 years or so. This is what's shown by this line over here. So that if you have a particularly strong engine sitting in the middle, you see that actually you get on timescales of 10 years, a dispersion measure of 1,000 just within the supernova ejecta. Clearly not what we observed in the repeater. So you don't want this to mirror that. There are a couple ways around that.
So what's the cooling time for we have ionization, we can also have recombinations. What's the
Yeah, so actually these calculations assume ionization recombination equilibrium, which is valid within these timescales. On timescales longer than 1,000 years or so, that would not be valid, but on these timescales.
It's a hard question. So it's the square root of the flux.
It's not stomach though, because it's not thermally ionized, it's ionized by photoionization. We need to know something about the spectrum and luminosity of the ionizing source.
And just where do you think the original repeater is?
I see. So I think the repeater is, in terms of the observations, it has to be way down here. In terms of timescale, I'll show in a minute that a limit on the dispersion measure, given that we don't see a large local dispersion measure, or more significantly, we don't see a change in the dispersion measure. And because the supernova ejecta expands with time, if a lot of the dispersion was within the ejecta, you'd expect to see a large change in the dispersion. We don't see that. So basically, you have some upper limit, which is, order unity here going down. And that actually limits the age of the repeater, which I'll show right here. So you can play this game and assume, what if all FRB engines are similar to magnetars that produce the luminous supernova? So by modeling the light curves of luminous supernova, the light like I showed earlier, you can infer some parameters about the magnetar in the center, such as its dipole magnetic field and spin period and things like that. And that tells you something about the ionizing radiation that it emits. So if we assume that the population of magnetars that produce luminous supernova also produce GRBs, then you get these tracks for each one of these magnetars. So each superluminous supernova, each magnetar gives you a different track here based on its ejecta mass and based on the properties of the magnetar for that particular superluminous supernova. Of dispersion measure as a function of time. And then you have the blue dots, which denote when the ejecta becomes transparent. This all happens on timescales of basically tens of years or so. And the observational constraints that want to satisfy the following. So first, you want to have an observational lifetime which is longer than the observed time scale, which is 6 years or so. Second, you want to have a dispersion measure local, which is less than what is referred to a local dispersion measure of the repeater, which is order 100 or so, 100. But more importantly, you want the change in the dispersion measure to be very low, because we don't observe any significant change in the dispersion. And this turns out to be the most significant constraint. And so the moment when each of these tracks satisfy all of these constraints, you get these purple circles. And basically, you see that all of these supernova predict that their repeater would have to be of order 30 or 100 years old or longer. And again, this is assuming a very strong ionizing source. These are magnetars that produce supernova. If we invoke a different kind of magnetar, such as one that produces the GRB, you actually have significant less polarization, and in principle, the repeater could be. So this is how one way you can limit the age.
Do these supernovas change the overall energy budget of these, like does the kinetic, like the whole thing changes, or is it only the observable light curves that changes?
Yeah, so the amount of energy dumped by the magnitude of these supernovas is order of 50 words. So it's
10 times that of what
10 times what
collapsed
you'd expect for a regular core collapse supernova, and so it accelerates the ejecta within to higher velocity. That's why the velocity of the supernova are more like 10,000-ish or higher kilometers per second, and goes to several thousand kilometers per second. But yeah, it definitely changes the ejecta.
Just to see if I understand the big picture, normally the 1051 comes from the energy of the formation of the neutron star, out of which 99% goes out neutrinos and doesn't help you. And the fuse that domain is basically what gets the shock going. So here you're going to store, and that collapse, instead of having it all be lost by neutrinos, and 10% gets to paint the magnetic field, I guess. Like this.
So besides, I mean, this is in addition to the neutrinos. You still have the neutrinos.
Of course, but those you don't see. Those don't help you. They don't
right,
power
exactly.
anybody.
Don't help you. So in addition to that, you have rapid rotation, and just the rotational power of this object. If it's rotating at millisecond periods, if you have a neutron star, rotating at millisecond periods, you have 10 to 52 words of rotational energy. And if some of that is dumped through magnetic dipole radiation, if you have strong magnetic field, then it can be dumped through magnetic dipole radiation to the environment, then you get rid of that.
So the field is only a conduit. It's not a storage.
Right. So this, in that respect, it's actually, I didn't go into this, but in that respect, these magnetars are somewhat different than the galactic magnetars, which we think are powered by exactly that. There's somewhat different. Okay. So moving from the supernova ejecta and what that tells us about the age, I'll go into a bit of the modeling of the nebula itself. By the way, so when did we start? What do I have? So I keep on track of
We will stop at 2:40.
2:40. Okay, cool.
2:30.
30.
And then we are having this for free.
Very good. So in a recent paper, we sort of tried to model this Clarion, this nebula here, and see and try to see more quantitatively, not qualitatively, if we can really get the right rotation measure and persistent source luminosity spectrum, which is sort of non-trivial, as I'll show you. And so the model that we had is, extremely naive and simple. It's just a one-zone model, so it's not even one piece. You have one zone for the nebula, and you inject some energy into it as some power law. So one of the three parameters of the model is this power law, alpha, which describes how you inject energy into the nebula. So some measure of the magnetar activity. You also inject particles, so electrons and protons, into this nebula, and we assume, the very naive, most simple thing that you can do is that the energy per particle is fixed. So you inject a number of particles that is proportional to the energy that you inject. And actually, this parameter chi, which describes the energy per particle, is somewhat constrained. So it has to be larger than about 0.2 GeV, because that's the escape speed from the neutron star. And it has to be about smaller than about 10 GeV, and that's based on modeling of the giant flare from SGR 1806, which was shown to have, from the afterglow, was shown to have a significant baryon mode. Maybe, yes. So there might be there's only a small parameter space for this experiment, but it could be that this upload is not strict one. So if you just take, this chi value close to the escape speed, so close to the minimal value, and you think that these shocks, basically as they collide, thermalize, then you get a mean Lorentz factor of the electrons, which is of order 200. And it turns out that that is sort of the right number you need in order to get synchrotron radiation at the frequencies that we see. What did we actually solve? So we just solved this simple one-zone equations involving the energy inside the nebula, and more importantly, is the particle distribution. So the only sort of non-trivial thing here is accounting for how the electrons evolve with Lorentz factor. Basically, as they emit synchrotron radiation, how they cool adiabatically, and evolve from this initial, presumably Maxwellian peaking at 200 or so Lorentz factor, how they evolve with time. And that's this equation here. So this cooling term encodes all the interesting information formed by adiabatic, synchrotron, Grunstone, and reverse quantum. And the goal is again to calculate the rotation measure and the synchrotron luminosity. So this is just one movie showing sort of an example of how these results look. So what I'll plot here is the distribution in Lorentz factor or gamma beta, whatever in Lorentz factor in this region of interest. This is the particle distribution, the electrons are distribution. Here you'll see a tick that basically says how time lapses. This will move logarithmically, so it will evolve quite fastly. And then at the bottom, you see the synchrotron luminosity emitted by these very same electrons. And this is the function frequency. And here are the points which have different colors, are basically the persistent source for the repeater. And the different colors you'll see as like the movie that different colors pop up on the electron distribution. So basically it'll tell you which electron with which Lorentz factor is currently contributing to emission at this so that's sort of the initial inflation of the bubble. Not very interesting currently. Disregard that. You see that you have this nice synchrotron peak that has prominent self-absorption. The reason the synchrotron luminosity falls down here is self-absorption. And that creates a pileup of electrons near the self-absorption frequency. I'm also showing the synchrotron cooling frequency and then inverse Compton cooling frequency. You see that at late times, after a couple decades or so, this black line just matches an analytic solution, which is an analytic solution that you can get for assuming purely adiabatic cooling. So even though at early times, synchrotron and inverse Compton cooling are very important, at late times actually we just assume that everything cools adiabatically. You get a very nice, simple solution. And the nice thing about it is that the distribution of particles tells you something about the injection rate of particles. So I have this alpha parameter here, which if you remember is the same parameter which tells you how E dot falls with time. It's just a single parameter that sort of comes in again.
So for the most of the energetic particles, how do the gamma rays compare with the size of the
so the lumber radius is smaller.
Now, initially, you're injecting both electrons and photons at Lorentz factor of 100?
No.
No.
So, electrons at Lorentz factor 100, you assume basically equal energy in photons. So you assume that the thermalizing you have, half the energy goes into photons, half the energy goes into
thermal.
This is just sort of a sample. So what are the model constraints? This is sort of one way to think about the constraints on the model in terms of the nebula. So what I'm plotting here is the age of the nebula versus the size of the nebula. And also give this angular size, gives things the distance. And so the constraints are the following. In terms of age, you have a lower limit, obviously, from the 6-star operational baseline, so you this red curve on the bottom, so you have to be above this curve. You also have a lower limit just based on the arguments that I gave before from the local contribution from the supernova jet to the dispersion measure and C3 absorption. And that is this dashed curve here. This can move a bit up and down depending on the assumption of what type of supernova was created and what type of magnetar was created. So that's in terms of the lower limits on age. We also have an upper limit on the age, which is basically an energetic consideration. You see some luminosity for the persistent source, which is 10 to 39 or so per second. Divide that by the total energy budget that the beam magnetar has, or 10 to 50 years or so maybe at most. And you get some upper limit on the age, which is the border of 1,000 years. Of course, this assumes that it's basically emitting at the same luminosity at all times, but it's more or less sort of an order of magnitude estimate. In terms of the size of the nebula, you have the following constraints. So you have a lower limit based on the fact that there's no very clear discernible self-absorption at 1 or 6 gigahertz, depending on exactly what you want to take. So it's very cool that there is self-absorption. The model does predict self-absorption, but given the current data, it's hard to say exactly where the self-absorption is. Whether it's 6 gigahertz, 1 gigahertz, sure that's not far from where we're observing, but it's not there exactly where it is. But whatever you assume for the frequency of the self-absorption gives you some lower limit on the size.
Where do you collide with like a lot frequency would you?
At what frequency?
Yeah.
I'm actually not sure. Well, I mean, it's an easy calculation, but yeah, not sure. And then you also have an upper limit just from VLB out imaging, which gives you a constraint on the size. So, That's about 0.2 milliseconds in diameter. And you asked earlier about the velocity of this nebula. So these dashed curves are basically the velocity of the nebula. And if you want to fall within this region of parameter space, you have to have a velocity of, basically 1,000, maybe 10,000 kilometers per second. So what we have to do with this nebula model is basically at a given age and size of the nebula, which both fall within this region, we also have to explain the rotation measure. This is a nice, the nice table from Daniel's paper. And we also have to explain the persistent source luminosity and spectrum. So we have to do all of that. And we only have more or less 4 key parameters in the model. Total energy budget of the magnetar, this alpha parameter, which tells you, how fast the energy is basically, how fast the energy is put into the nebula, some initial time scale, and some velocity for the nebula. And so we don't have a lot to go on. It's actually not trivial at all that you can satisfy all of these constraints with only this limited type of modeling. So even though the problem is highly constrained, it turns out that there are solutions. These are by no means fits to the data. There's absolutely 0 fits performed. It's just running the model with different sets of parameters and seeing what sort of more or less works. And so what you see here on the left-hand side is the rotation measure as a function of time. So initially, sort of just goes up, we inflate this nebula and populate it with particles, and then it sort of drops down, and you have sort of a nice analytic power law that you expect it to fall off with. And what we do is the moment that the rotation measure reaches the observed value of 10 to the 5 radian meter squared, we call this, the age of. I see. So you inject energy and you assume some magnetization parameter, some sigma that basically tells you how much of it to do some ordering of it because it's random. Yes. So that's a very good point. What we assume in the model is that basically we evolve the magnetic field as if it's a random turbulent magnetic field. But in order to get a significant rotation measure, we actually do need some coherent length scale. That's a whole separate issue, but it is one problematic issue. I can go into that later. So then if you look at, at this stage and zoom in, what happens here, and actually plot the data from Daniel's paper, and the rotation measure, you see these black points. You see that, there is no fitting attempted here. You see that more or less you get sort of a secular decay that, roughly agrees with the data order connected. And then you can do the following thing. At the time when the rotation measure is 10 to 5, and you get sort of the right rotation measure, ask yourself, what is the luminosity of the persistent source in the spectrum at that given time? So again, at the same t age, these are the solid curves here. Just take these models and plot the luminosity. What do you get? Turns out that you can get something that's more or less consistent, passes through more or less the right parameter region in terms of luminosity and in terms of spectrum. And again, all of these models have a self-absorption turnover, which is sort of within or close to the band that we're trying to observe. So again, these are not fits to the data, but this is sort of a proof of concept that the model can work with a limited number of parameters. What do we learn from this? So first, we learned that the solutions require a large energy reservoir, sort of pushing the upper envelope of what we feel comfortable with. So you need an energy of upwards of about 10 to 50 Hz, which implies an interior magnetic field in the magnetar upwards of several times 10 to 16 Gauss. May be possible, but sort of starting to get in the uncomfortable limit. Another thing that we learned is that we need some decay of the energy injection rate. So if you just assume that the magnetar inputs a constant energy injection rate, same amount of energy at a given time, you can't reproduce the data. And the reason is that you need a population of electrons injected at early times that will have enough time to cool and to contribute enough to the rotation measure. And so this again shows that not any set of parameters works. You can't just throw anything and anything will work. There are certain constraints that come from this type of model.
Is the shell accelerating or decelerating? Is the contact, let's say, the contact?
So the nebula in our model is just expanding at a constant velocity. That's not what we actually expect to happen. We expect it to accelerate as you inject more and more energy.
Probably inject rate is going down, but you've got a bunch of depends on how quickly you inject.
Yes, it does depend. So there's these different self-thermal solutions. If you say would inject a constant energy injection rate, it would accelerate as t to the 6/5. If the energy rate decays, then it would be something a bit different. So it's possible to go through that.
Then you're unstable just the way crab is. really tailor the convection.
Yes, you would expect this to be an unstable variable. Yeah, certainly.
And if you have magnetic fields, would you still be unstable?
Yeah.
If you have magnetic fields, it could be a sort of.
Yeah, it could be that magnetic field like some stabilization. So I'm not, it could be that it's not entirely clear that.
But what is the principle, initial principle T0?
So T0 is sort of, in some sense not an interesting parameter, but a necessary one. So basically, we assume that's the time when we start injecting the energy. So you just assume a power law injection. So in order for that power law to not go to infinity, you just assume some initial time when you start injecting that. That's it. Yes, there's infinity. I didn't write that down, but for these models, we take something in the order of a couple months or so, something like that. Okay, so what are the model predictions? Actually, many of them. So the first thing is that we expect correlation between the rotation measure and the persistence source. Because in this model, they're both being produced by the same physical mechanism, by the same nebula, we expect them to correlate with one another. And so, you can get to different analytic solutions of how the rotation measure should decrease secularly in time, and how the luminosity should decrease in time, and you can get some rough ideas about the spectrum and maybe get some closure relationships. This is very cute to do analytically, but I take this with a grain of salt. If you actually look at the numerical models, there is some differences. In particular, if you're near the self-absorption turnover, which we think we are near the self-absorption turnover, then some of these things are not correct. For example, the power law at which the luminosity falls off is not actually true if you're at this peak. At this peak, you see the spectrum, the luminosity not fall very much. And so all this should be taken with a grain of salt, but in principle, we can work with that. Again, self-absorption turnover in all of these models you'd expect to be quite close to the observing band, so around 2 gigahertz or so, which seems to be consistent with what Sarah mentioned earlier, broadly speaking. And then the last thing which I'll point out is that we'd expect sort of somewhat skeptical, this is a bit out there, but you'd expect within this model that if the engine activity follows the energy injection rate, then the distribution of rotation measures at which you find different FRBs is distributed more or less logarithmically flat. In other words, you basically have roughly the same chance of finding rotation measure, an FRB with 10 to the 5 rotation measure and 10 to the 2, and 10 to the 1 or 0. And you can put all of that into a plot like this. So I think I'll skip this, but if you are interested, I can run this later just in terms of time. But this is basically, if you observe an FRB with a given dispersion measure and a given rotation measure, you can give some predictions as to the luminosity of the persistent source because of this correlation. So that's the idea here. Okay, so summary, or what I call a current state of affairs. So first thing, are there multiple populations? As I said earlier, maybe, I wouldn't be surprised, but I don't think there's any convincing evidence for it yet. So I see no reason to start going down that path until we do have evidence for it. Current observations are extremely constraining for any model. The model that I just presented here is somehow I'm trying to convince you that it works, but it's actually quite amazing that it does work. And I think if you go just qualitatively through a lot of the other models, definitely, many of the cataclysmic type events and things that have been proposed many years ago, most of them are just ruled out immediately by the observations of the theory. And so throughout this notion of more theories in verse, I think that's something we should forget about. In my bias, there are only a few currently proposed models. Obviously, people should propose more models, and maybe we'll have many more in the future. But of the currently proposed models, there are only a few that withstand these tests. And I think we're only at the very beginning of developing quantitative and predictive models, which I think is an important step, just going beyond this qualitative level of, okay, maybe you get the right frequency, maybe you get the right time scale. I think we should try to develop more predictive quantitative models. And as to a look to the future, so again, just my 2 cents. Obviously, I think there's a lot of science that can be done with large sample sizes of events, and I think hope that time will give us that. But we should lose focus on finding a few well-characterized sources. Again, almost everything that we know currently about FRB just comes from this one source, the repeater. Hopefully, we can now learn much more with the second one, but you know, the idea is if we can localize more events, find their host galaxies, their environments, we can learn much about the progenitors, even if we still have lingering questions about the emission mechanisms that prevail for years to come. I think there's a bright future ahead. I think that's pretty clear, just given by this meeting and the number of people interested in working in the field. You know, facilities like China, SCAP, RealFast, it provides so much more observational data, and I think theorists, myself included, we need to meet the challenge and really up our game to develop more quantitative predictive models. And the last thing is that following through from what we've learned from supernovae and neutron star mergers, you guys heard Rosalba's talk yesterday. She discussed things that we can learn from neutron star mergers. I think we should also focus not only on the question that I presented here, which is what are FRBs, how do they work, but also on how can we use them, what can we learn from them, and how can we use them to answer some broader questions. I think that's sort of a very nice segue into the next talk. So hopefully we'll hear more about that. Thanks.
So there are many super luminous supernova that are cataloged over the last 30 years, and you make a prediction for how every one of them evolves in the radio. Yeah, people
have been looking at supernovae in the radio. At the moment, there are only a couple radio detections, and mostly non-detections.
Can you answer my earlier question then about how the 121102 the system data sort of stacks up against this known radio counterparts of supernova?
So again, I'm not sure how radio supernova. I'm not sure about the greater supernova. From my recollection, if I remember correctly, I think this would be a complete outlier. I think this is an extremely luminous source that is not, nowhere. I think it's definitely above the luminosity of radio.
It's starting to get interesting though that you don't see a really bright radio source.
True. It's very interesting. So the thing is, with most supernovae are at much further distance than, say, the repeater. And so you might have trouble observing in most cases, but there are a couple of examples where there are nearby ones and that are well observed, and there are off limits. So that can be pretty important.
Regarding your Occam's razor, the one thing that people often point to regarding what might distinguish the repeater from the other FRBs, aside from the fact that the pulses tend to be a bit broader. And looking at this beautiful data that was just presented, that seems to be even more, as the authors I'm sure must have all determined, even more of an issue with that source, right? So, so is that emission, or has it some type of propagation, right?
A great question.
If it were a propagation effect, in the Clarion picture, it's a little puzzling because, repeaters you would think would be younger and more active. So nebulae would be smaller. Therefore, propagation effects would usually be more confined in time.
More confined in time? Well, the density would be higher, so
the density would be higher, yeah.
I'm not sure exactly what the trade-off is. I'm not sure about that, but it's certainly a question that needs to be answered.
So we have had a couple of magnetar nebulae in our own galaxy. Only one of them, 1806, was well studied. So is your claim from this that nebula would also be a baryon-loaded nebula and not a electron?
Well, yeah, our logic is kind of the opposite, but yes. We're using the inferred modeling of 1806, claiming that it's not crazy to think that these players in extreme cases can inject an electron. So you do need somehow to excavate matter from the surface, which is at first glance kind of crazy.
Well, that's what we saw in 1806 with lost it off the mass of an asteroid.
Yeah.
So do you predict secular polarization for the system?
I haven't thought about polarization actually. I haven't thought about that aspect.
I mean, you never see them for normal pulsar manipulation.
Yeah, that's a good point.
Sure.
So if you have alternating magnetic fields there, and you have you can have multiple propagation of the incident photons, and this could destroy the polarization because you can possibly, like you start with some infrared, each one passes through a different color. They see a different magnetic field, they have experience different period rotation, so by the time.
Right, so if you had a completely random field, you wouldn't expect any rotation measure, which is why
I
you
don't know about
some
everything.
coherent large scale field.
You could lower the polarization.
Right.
Depending on
So basically, rotation measure is governed by the lines of the first, I assume, right?
And even the positive, this medium.
Well, the persistent source, like the linear will all be depolarized because of what you say. However, I think what Brian mentioned is the circular doesn't care. Well, I don't know if the circular cares or not, but it's.
Yes.
So the energy injection rate at a function of time. So the measurement is shallower than metal.
Right.
What percent?
So, yeah, I actually should have maybe had a slide on this. So the point in this magnitude is that it's not, I mean, the model for this magnitude is that it's not rotation power, it's not spin down. So you wouldn't expect to the -2. It's probably governed by dissipation of magnetic, internal magnetic energy. And I don't think there's, as far as I know, there's not a very clear prediction as to how that evolves with time.
At early times,
Yeah.
The energy source.
you need to know what the initial magnetic field is, etc.
Energy source for the there, which produce the pulse itself, is also due to the magnetic field.
Yeah, so it's the same mechanism. You have dissipation of magnetic field that emits the flare, and that populates the number.
It's not the pulsar still.
If you put all these constraints that you got from observation into your model and solve it, so you can basically make a prediction when you're going to see the next steps, after that the next, and you can make basically you should be able to make predictions about any of our data that there is going to be.
So, yeah. Well, no, not given our simplicity of this model. So this model doesn't actually assume anything about the burstiness of the flares.
Yeah, because I didn't see how periodicity.
Yeah. So again, what we assume is a constant power law energy injection rate. In reality, the picture that we have in mind is that you have successive bursts. That's what produces FRBs and what makes them positive and what makes them bursty. And these happen sort of sporadically and in a non-close-linear fashion. But that if you take the envelope of that, that would maybe follow some sort of amount times power law. That's the assumption here.
But you expect no periodicity, right?
Yeah, so in this model, we expect no periodicity because spin is basically unimportant here. There are some variations where you could add spin. Spin might be important in terms of a large scale coherent magnetic field, so maybe you do need to think about spin, but in this prediction.
But I don't see why you can't basically repeat this process over and over and see the people and then trigger, send a process in and see that already the magnetization has peaked up there, that we have this electron, the population is actually waiting, like send the next trigger and see.
In principle, you can do that. The question is, how do you eject these flares? Like with what frequency, with what energy? That would be sort of some assumption, some big unknown question mark in the model. Oh, I see. You're saying take the observations of the pulsar. I see the point.
Because you have all these observations and you can repeat them, so you can keep them into your model and you can tell us how often this process is basically happening, and you should be able to explain this, the source of energy that is basically supplying at that rate. Because sometimes you see the repeater, I'm not an observational astronomer, but I see that in 10 minutes you get the chunk, that's keeping fast.
Right.
And then there is nothing. And what is this source from
So again, I don't think our model, sort of an unknown, I don't think I'd be able to predict why, the bursts are clustered and then not. But if you're saying the opposite, if I use the observations and sort of inject bursts like we observed, that's something that in principle could be done. The only caveat is that this model is sort of sensitive also to the entire history of the nebula, not just what's happening currently. So in particular, for example, the rotation measure care about electrons that were injected for the long term, but not just what's subjective.
I have one last question. So based on what I didn't understand the whole thing for some people, but based on what I see, this model is based on magnetic. So if you dig into any repeater, like the second one, and if you basically increase the sensitivity of your observation and realize that all of our these are repeaters, you must detect the very bottom magnetic for each singular FRB based on this. Because if you don't work with the magnetic field is not.
So the point is the following. Intrinsically, I'd expect all of them to be magnetic. In terms of what that manifests observationally, that's not actually that clear. And so in this plot, you see different rotation measures. So this is the repeater, and this is the Masculi burst. Just plot those two because of the larger rotation measures. And what do you predict for the persistent source? And so for all of these, you predict some rotation measure and some persistent luminosity. But
there's some magnetic and some motion there.
yeah.
Explain that, and that's a very general thing. There you have that 3D lines. If that's the message, and there's a magnetic field, you should be able to basically explain some of that.
Yeah, but the point is that sometimes at certain parameter spaces, the magnetic field drops so substantially that you wouldn't expect any detectable counterpart or any significant detectable rotation.
But if it drops up, and you basically explain that electron density that you need to basically initiate,
Oh, so at earlier times you had a larger field, but at the time at which we're observing bursts number X, a given burst in the sky, it's equally likely to have a rotation measure of 10 to the sort of order of magnitude or the unity, Rm as it is 10 to the 5. Which means that we're observing this burst when it's much older. If it's again a repeater.
you're going to capitalize on that.
Yes, exactly.
The ones that are in the same iteration have the same.
Exactly.
Excuse me, we are a little bit late for our schedule, so we can move to our more discussion in the panel discussion later. So let's thank again.